We are now at the end of chapter 5. We're looking at the last section, which is 5.6. And as we can see from this opening slide here, chapter 5 has been all about trigonometric identities. We began with the sort of fundamental identities, the simplest of which is cosine squared plus sine squared equals 1. And then we moved forward from that through a bunch of other identities. And the last thing we just talked about last time was the double angle formulas, which we got directly from the sum and difference identities. We looked at the double angle formulas for things like cosine of 2x or sine of 2x and how you can get those values based on just sine x functions, just single angle formulas. So the double angle formulas were last time. And so now, in the final section, we do half-angle identities. So half-angle identities and their applications. So just to sort of help with this labeling, and we'll sort of see it when they give us the formulas, but for the double angle, that's where you have sine of twice a particular angle, and then you have a formula for what it would be in terms of the original angle. And if my memory serves me right, this was 2 times sine theta cosine theta. But just to get the idea of what the label means or what the identity helps us do, it basically says if I have, I can get the sine of twice an angle using an expression that has the angle itself. So I can get sine of 60 degrees by using a 30-degree angle. I can get sine of 100 degrees by using a 50-degree angle. Because if I had 100 degrees over here, then if that's twice theta, then theta would be 50 degrees. And so this is the idea behind the double angle formula, is that you can use it when the angle that you're trying to evaluate is double an angle that you want to be able to use. I don't know if that helps to make sense, but at some point we want to sort of delineate these two. So now with a half angle formula, how is that going to be different? So the half angle formula will be when the sine function we want to evaluate is half of an angle that we can use. And then we're going to have some expression, which we'll see the formula for it here shortly, where in the expression, you just have things involving theta instead of theta over 2. So in both cases, just to keep it simple, you have an expression where you're using theta, and that gives you an ability to evaluate for the double angle formula, something that's double theta, or for the half angle formula, something that's half of theta. So if you know sines and cosines of 30 degrees, the double angle formula would allow you to use those to get 60 degrees. And the half angle formula would allow you to get 15 degrees. So if theta equals 30, then half of theta would be 15 and twice theta would be 60. So having the trig functions of 30 gets you double that angle and half of that angle with the double angle formula and the half angle formula corresponding. So that's the idea of the names and what these manipulations allow us to do. And of course, we'll see that more with applications and practice problems and things like that. All right, so they actually did like they did way back with the sum angle formulas. They begin with a justification of the formulas that they get. And I'm going to do like I did before, because I do think that's in the best interest in the students in these shorter Zoom sessions. I'm going to skip over why it's true, and let's get right to the identity where it says what's true and practice on how to use it. So we'll look at it as we scan through it. But it says basically we can use the cosine sum identities to derive half-angle identities. And so they sort of give a little expression of how they do that, and they talk about it. And they end up basically solving for what that half angle would have been compared to twice the angle, and then they get their formula. So in this first case, they basically end up where the cosine of x is equal to this expression involving 2x. So here's cosine of x, and in the expression is only twice that angle. That means the x value in cosine is half of the x angle on the cosine on the right. On the left, you have x, on the right, you have 2x. So then the angle on the left is half the angle on the right. And then they say, all right, let a equal 2x and replace, and then you get this half angle formula. So anyway, I don't think it's too helpful to concern yourself too much with these derivations. And then, of course, if you have sine and cosine, then you can use both of those to get tangent. But here's the summary of the formulas themselves. So I'm actually going to start sort of almost halfway through the slides here, where we look at the formulas themselves, and then we practice on, think about how to use them and what they say. So I will point out that these formulas are certainly for the cosine and sine, they're not as nice and simple as the earlier formulas for cosine and sine, because they have this plus or minus square root in them. And the basic idea behind that is that if you have an angle and you're trying to find out the value of the function for half of that angle, well, depending on the angle, you don't know which quadrant you're going to be in. So you don't know whether the x or the y value will be positive or negative, even if you can determine its amount correctly. So that's why we have this plus or minus. So I'm just pointing out that you have this plus or minus. So you have a formula to try to calculate cosine of a over 2, but it's not giving you a specific answer. It's saying, well, there's two possible answers, positive or negative. So that means you would need to know more information about the angle A. You'd need to know something more about angle A. If you cut that angle in half and you want to get the value, you would need to sort of know which quadrant you're talking about or something like that. But anyway, we will see this come up as we use the formulas. But the thing to point out here is that we have a formula, but there is a plus or minus square root, and we have to keep that in mind when we're applying it. Now, the nice thing is that the tangents shows up with this multiple ways to get the tangent half angle formula. And then in this case, notice that in all the formulas, tangent is not involved. In the first formula, it's only cosine. And in the next two formulas, it's cosine and sine are both used. And then when you have both of those, they're much simpler. So the half angle formulas for the tangent are quite nice and easier to use and provide a pretty simple formula for the result. All right, so just looking them over like this, let's imagine that we would just look back to this list of what they are to think about how to use them on the problems that we're going to look at for examples. So in example 1, using a half-angle identity to find an exact value. So they tell us to find the exact value of cosine of 15 degrees using the half-angle identity for cosine. And so again, what does this allow us to do? It allows us to say if the result that we want has in the angle an angle that is half of an angle that we know the result for, then we can evaluate the half of the angle that we know using this formula. So in this case, if a over 2 is 15 degrees, then that would be half of 30 degrees. So this leads us to 30-degree angle for the half-angle identity for cosine. And so if we're then evaluating cosine of 15 degrees, we recognize that cosine of 15 degrees is the same as half of 30 degrees, because in this formula, it's written as a over 2. So that would tell us that the A angle is 30 degrees. And so in the formula for A, we plug in 30 degrees. So up here, if a over 2 is 15 degrees, then that means the A value over here was 30 degrees. And that's the idea of how this formula allows us to use it in this case. Because we know the cosine of 30 degrees. And this gives us a way to find cosine of 15 degrees, knowing the angle, knowing what we get for cosine of 30 degrees. So that's kind of the idea and the way to think about when and how this thing is used and how it helps us. Questions about that?
Why would we use this over the cosine difference identity?
Of the cosine what?
Cosine difference identity?
Oh, difference, yes. We could do that too. We could absolutely do that too. Then we would say, how can I express 15 degrees as a difference between two I know, like between 45 and 30, as an example. And we could do that. But I think what you'll recognize here is that this is quite a bit simpler. Does that make sense?
Yeah.
Yeah, so definitely this is not the only way you have to do this. And in some sense, as they said in the beginning, this was derived from the sum or difference formulas. So some of these identities aren't the only way to go. It's kind of like algebra, where there's different ways sometimes to solve an equation in algebra, or different process to go through. Do I simplify first, then do I isolate X, or do I, and so there will be different identities that can be applied to any particular problem. And what we should see is that since they're all valid, if you did this different ways, they would all come up with the exact same answer. And if they do come up with the same answer, that's a confirmation that they're all working and that they're all giving you true, valid things to use. So once that's the case, you could then say, all right, well, which one's easier? Then it's a matter of choosing which one is easier, if that makes sense. So that's a good point and a good question. Other questions at all so far about this motivation for using this? Yeah.
Do we also learn like a scale of cosine x equal 1 plus cosine 2x over 2?
Our square root?
No, scale, like a square, just a scale.
Oh, square?
Square
Yeah,
cosine
absolutely.
x equal.
You could use this by squaring both sides. So I think that's what you're saying, right? Do we recognize that another way we could see this? And so I think that's good to see, that you could take all this stuff on the right and square it. And that would mean that you would be squaring this side too. And that would give us the cosine squared of a over 2 as an angle would just be 1 plus cosine a over 2. Because if it was a plus or minus after you squared it, it's just going to be that value there. And that has to be a positive value. That can't be a negative value. So that's definitely a way we could use this. Now, we wouldn't say that that's a different identity because it's so close to this one. You can quickly modify this one to get that. But absolutely, if you were tasked to find the square of a cosine of a half angle, then that would be even easier thing to use this identity to get. Does that answer your question?
I mean, like when I learned this at the Korea, like I learned like a square cosine x equal 1 plus cosine 2x over 2, like that.
Yeah, that's absolutely value too. That's the same thing we have here with a little variable insertion. The thing I would point out about what you just said that you learned is that neither side of that has a trig function that's isolated. Right? So that's something that you can remember, but that doesn't sort of say that that's a half an angle for cosine. That doesn't say that that's a double angle for cosine because you haven't solved either one. So if we're trying to collect identities and label them, then we call this a half angle identity because it tells me how I can get cosine of half an angle. But if I have this side squared and the other side with a 2 in it or something like that, then neither one is isolated. And so we really do this so we can sort of label what our identities do for us. And then we can always modify them a little bit, something that's equivalent like what you said. Does that make sense?
Okay.
Yeah. Great questions. All right, so how would we then follow through? We're supposed to get the exact value of this. Well, we would plug into the formula and we get cosine 15 degrees is equal to cosine 1/2 of 30, which means we can take the square root. Now, they're saying right here, choose the positive square root. They didn't put the plus or minus there. So how would we know to do that? Well, we would recognize that 15 degrees is in quadrant 1. So what I was saying before here is that the way you typically will resolve these angles is, look for the quadrant of angle A divided by 2. If you know that A divided by 2 is in quadrant 1, then you know that the cosine, the x value, will be positive. If you know A divided by 2 is in quadrant 2, then the x value, the cosine of that point, would be negative. So then you would take the negative of the radical. And so if they're telling you what the angle is, well, then you can say, well, I can look at which quadrant that's in, and then I know whether to choose the positive or the negative square root here. This formula works no matter which quadrant A over 2 is in, but the way it works that way is by allowing you to choose the positive or the negative root depending on which quadrant it would be in. So in this case, they didn't put the plus or minus, they just left it off and left the positive radical because they're recognizing that 15 degrees is in quadrant 1, and the x value of any point in quadrant 1, which is what the cosine refers to, is going to be positive. So then we're in a position of just simplifying. So they evaluate the cosine 30 degrees because we know that, and they get this square root of 2 over 2. And now we're going to get expressions that look kind of funky here. So look, we have a square root underneath another square root. The square root of 2 plus the square root of 3, all divided by 2. But that is an exact value. You could just type that on a calculator and it would approximate that to whatever level decimals you want, or you can leave that expression as it is, and that's the exact value. So for most students at this very point in this class is the first time you usually ever came up with function values that looked anything like this, that had this sort of weird root inside of a root notation. I just want to acknowledge that and point that out, that looks uncomfortable. It looks like you feel you really should do something with that, but we just leave it. That's the exact value. And you can always then type that in a calculator if an approximation is needed. All right, so let's continue. Here's another example, example 2. Using a half-angle identity to find an exact value. And in this case, they want the exact value of tan of 22.5 degrees. And it says use this identity, and they give us one to use. So one of the things to point out here is that they've switched now, they've switched to tangent instead of before we were at cosine, but they're still using degrees. Now we could also have radians here. So maybe they could have used radians if they wanted to. Maybe they could have said, find the exact value of tan of pi over 12. And then you'd say, oh, that's half of pi over 6. So I can use the half angle identity with pi over 6 to get pi over 12, something like that. So in this case, however, let's still work with what we got. So we have 22.5 degrees. So if that's a over 2, that means that the angle we'll have that we'll use in our formula would be double that, or 45 degrees. And that's an angle for sine and cosine that we know. And I'm pointing that you sort of have to mentally do that because they just kind of automatically did it over here in this line here, in the second line. So they're saying, all right, we're going to use this identity above. So the tan of 22.5 degrees, we're recognizing that 22.5 degrees is 45 degrees divided by 2. So that's in the form a over 2. And therefore, a would be the 45 degrees that we would plug into the formula above. So that gets us to this expression to match up with here where we've plugged in 45 degrees for a from the identity. And as I said in the beginning, kind of an interesting about the tan half angle formulas, they end up using sines and cosines instead of tangents. So sine of 45 and cosine of 45 are both square root of 2 over 2. So they take those two function values and they swap them out with a square root of 2 over 2 in the expression. So now that expression with a big fraction with little fractions in it is a complex fraction. And as we've seen before, algebraically, the way to simplify a complex fraction is multiply by a 1 with the lowest common denominator of the little fractions in the top and the bottom of the 1. In this case, the little fractions both have a denominator of 2. So they're multiplying by 2 over 2, because when you multiply through by the LCD of the little fractions, all the little fractions denominators are wiped out. So when they did that in the top, the 2 whole number 2 cancels with the denominator of 2, leaving the square root of 2 in the top down here. And when they do that in the bottom, they had to distribute to the right and the left term. 2 times 1 is 2. And again, 2 times square root of 2 divided by 2, the 2's cancel, leaving you square root of 2. So then, now that they had this fraction, our work is still not done in the simplification department, because now we have a fraction that has a radical in the denominator, and you want to rationalize the denominator. And so the denominator is of the form a plus b, where one of those is a root. And so you multiply by the conjugate, a minus b. So if you have 2 plus root 2, to clear out that root in the bottom, you're going to multiply by 2 minus root 2. That's the conjugate. But whatever you do to the bottom for multiplication, you have to also multiply on the top. So that's why they're multiplying by 2 minus root 2 in the top and the bottom here. So then in the top, you have to distribute. So you have 2 times square root of 2. And then you have square root of 2 times another square root of 2, which is just 2. So that gives you the numerator that they have below there. And then on the bottom, when you multiply a minus b times a plus b, where in this case a is 2 and b is square root of 2, then the pattern you're setting up is where you get a squared minus b squared. So in this case, a is a 2, so 2 squared gives us the 4 over here. And then the square root of 2 gets squared, giving you just the 2. And that's how we eliminate the radical in the bottom, by multiplying by the conjugate. By setting up the a plus b, a minus b pattern, you get a difference of squares, everything gets squared, and the root goes away. Well, so once the root has gone away, then we can simplify that denominator by just doing the subtraction of 4 minus 2, getting a 2 in the bottom. But then we have a common factor. So there's just 3 stages of simplification in this answer here. We have to then recognize that there was a 2 as a factor of both of the terms in the top. So they factor that out using factorization, because then that 2 as a factor of the numerator can cancel with the 2 that's the factor of the denominator, getting us all the way down to this final simplified answer of square root of 2 minus 1. And we can compare that to where this started before all of the algebra stuff happened. So we started with this thing as our answer. And then after getting rid of the complex fraction, and then using the conjugate to get rid of the root in the bottom, and then factoring the 2 out so we could cancel the 2 out of the top and the bottom, we got all the way down to this final answer in its simplified form of square root of 2 minus 1. And so here was an example where we found an exact value of half of 45 degrees in the tangent, 22.5 degrees, by using 45 degrees in sine and cosine. All right, so there's a couple of things I want to point out before we leave this example behind, because I think they're worth mentioning. One is that when you arrive, keep drawing, maybe I'll try a highlight. Let's try that. When you arrive with this answer here, yeah, that works better. When you first use the identity and get that answer, well, it's definitely not in its final format. You're going to have to somehow be able to do these steps to get it down to this format down here. In this case, it involved 3 different kinds of simplification. And the computer's going to want that. And if you don't have that, it's going to not be marked correct. And there's a lot of work in there. So there's a lot of places where you might make a mistake. There's just a lot of algebra piling up. Even though there's no variable at this point, this is all arithmetic. So because this is all arithmetic, they do ask for the exact value. So we can't just type this tan 22.5 degrees on a calculator. But what we could do is when we get this first step, where we have square root of 2 over 2 divided by 1 plus square root of 2 over 2, you could type that whole thing on a calculator. You have to be careful with PEMDAS there. And that will give you a decimal. And you can check that the decimal on your calculator for that big mess matches the decimal on your calculator if you just put in tan of 22.5 degrees. That will confirm to you that you've sort of initially used the identity correctly, plugged in the right angles, and determined the sine and cosine of those angles correctly. And so when they want the exact value, you could start by just putting tan of 22.5 degrees on your calculator and getting that approximation. So that would be something like, 0.4, whatever. And then as you go and try to use the identity, when you first plug into the identity and put in the angles, you could put that on the calculator and see if you get the same decimal. But you don't want to forget that you have to go through a simplification process. And then as you go through all the little buggery algebra steps to get that final simplified answer, you could then check that final simplified answer and also make sure that you have the decimal that your calculator has for tan of 22.5 degrees. So that was the point I was trying to make here, is how even though it says exact value and you can't answer the question purely with your calculator, the calculator does still serve as a tool to help guide your work, so that you're not completely going through all of this blind and just hoping your answer is correct at the end. You can check it on a calculator as well. All right, so let's continue. So now let's take a look at example 3 here. It says, finding values of S over 2 given information about S. So how is this different here? Just looking at what it says. So this is when you're trying to find the value of a half an angle when you're told something about the angle. And of course, when they say given information about S, it'll be what S would be in a trig function or something like that. So let's look at this first example. You are given that cosine of some angle S is 2/3. And you're told that S is in this case, between 3 pi over 2 and 2 pi, that's in quadrant 3. I'm sorry, quadrant 4. I said 4 and wrote, yeah. So then, given this information about S, the value of the cosine and which quadrant it's in, they want you to then find cosine of half of that angle. And additionally, they're going to say, well, if you can do that, then you can tell us sine of half of that angle and tan of half of that angle as well. So in this case, we're told cosine of an angle, and they're saying we can then find cosine of half of that angle. So that still goes back to this basic formula. We're trying to find cosine of half of an angle, and what we know is something about cosine of the angle, the value itself, and then if you know what quadrant it is, you can figure out about the plus or the minus. So that's what's going on here. But they're having us then translate to that, getting all of the trig functions that we would get off of that fact. All right, so if we have cosine of S is 2/3 and we want cosine of S over 2, then we would use the half angle formula for cosine. Well, they do point out that if angle S is in quadrant 4, which we pointed up above here, then we can use that to figure out where S over 2 would be. So if we have 3 pi over 2 to 2 pi for S, and we divide both of those by 2, because you're cutting the angle in half, then that gives you that S over 2 is between 3 pi over 4 and pi, which means it's in quadrant 2. So if you're given quadrant 4, look at the range of angles for quadrant 4, divide that by 2, and you see then that you have to be within quadrant 2. Now, in quadrant 2, we know that sine would be positive, because in quadrant 2, the y value is a positive number, while cosine would be negative, and therefore tangent would be negative, because again, in quadrant 2, the x angle is negative. I'm sorry, the x value is negative, the y value is positive, and the fraction of those would therefore be negative. So by seeing which quadrant is in, you can delineate all the signs of anything you're trying to figure out. And then they just said, all right, well, then you could use all 3 formulas. First, if you knew, if you know the cosine, you can use the sine formula where the cosine is required and plug in the cosine value, choosing the positive value for sine, because in quadrant 2 it's positive, so they don't put the plus or minus on the root, and evaluate and get the value for sine of s over 2. And similarly, we can use a formula for cosine, which just changes from the minus to the plus for the cosine half-angle formula compared to sine. And you can plug that in, and this time you use the negative number, because you know in the quadrant 2 the cosine will be negative to get that value. And then now that you know sine and cosine for tangent, you don't even need to use a half-angle formula anymore. You can just take sine of half the angle and divide by cosine of half the angle, since we just figured those out, to get tan of half the angle. And that gives you this down here, confirming that it comes out negative as it should. Now, one of the things I'll point out here is that what we knew in this problem was cosine. We knew cosine of s. So if we're trying to use the cosine to figure out these half angles, remember in our original formulas up here, that for the tangent, you had a bunch of choices here. And they ended up not having to use any of those because we had the formula. But for both cosine and sine, you needed to know the cosine. So that was by design that they gave you that. If they had given you the sine, then before using any half-angle formulas, you would have had to use the sine to turn around and find the cosine with a fundamental theorem like sine squared plus cosine squared equals 1. Both for cosine and for sine, the half-angle identities both use the cosine. And that's why for that problem, they gave us the cosine. But if they had given us sine of s and the quadrant that s was in, we could have used that to figure out cosine and then turn around and use the half-angle identities as well. Questions, comments, discussions about any of that? And this was their process that they used. So they used the cosine and the quadrant to then apply that to the first 2 half-angle formulas. And then since you knew sine and cosine, you just use that to find the tangent. All right, so let's see what's left here. Lastly, example 4, got about 10 minutes, that should work. They have a couple of different ones here, an A and a B, but they want to look at simplifying expressions that are using half-angle identities or using half-angle identities to simplify an expression. So an expression means that we don't have an equation, we just have an expression, and we want to think about how to make it simpler. Well, if you look at these formulas again with this in mind, again, I keep coming back because you'll just want to keep referencing these things to get used to them, see what they say. You don't have to memorize them. You can always look them up. But as you use them more and more, you'll start to perhaps remember them a little bit. That if your goal is simplification, if you have an expression that you're trying to simplify, well, notice that in every one of these, you're going simpler by going from what's on the right to what's on the left. Because you have some possible radical of a fraction that just becomes a sine or a cosine function. Or you have perhaps a fraction of cosine functions with a denominator that has a summation in it. And so that's simpler if you just convert that to a tan. So in these cases where you're thinking about if these could help you simplify an expression, it would boil down to recognizing if you have something like what's on the right, and therefore using the identity to convert it to what's on the left. So looking at example 4 at the end here, we have to sort of see if that's what we have. So for the first one in part A, they just give you this formula, this expression, plus or minus radical 1 plus cosine 12x over 2. So it says this matches part of the identity for cosine of a over 2. The plus means it's the cosine. If it was a minus, it would be the sine. So the thing we would be comparing this to is plus or minus the square root of 1 plus cosine a all over 2. And so if we compared it to that, this is what the identity is for cosine of a divided by 2. And so what we would want to recognize is that in the expression they gave us, 12x is a. That's the part in here, that's 12x. And so to convert that over to the left side here, we would substitute 12x for a. And that means over here, we'd have 12x cosine of 12x divided by 2, which they get there. And then, of course, we can simplify that by saying 12x over 2 is just 6x to get their answer. So the key to that is first recognizing that it matches part of the identity, that we have a plus or minus of a root 1 plus cosine of some angle over 2. And then we just convert that angle A into a 12x to apply the identity. So similarly, in part B here, we have something where if you just see it all by itself and it says to simplify, it's like, what do we do with that? Well, you could, for example, just to sort of show something different than what they have here, you could say that this is the same as 1 over sine of 5 alpha minus cosine 5 alpha over sine 5 alpha. And then we could write that as cosecant 5 alpha minus cotangent 5 alpha. Maybe that's a little simpler. Maybe that's something interesting to see. But instead, if you recognize how this looks like one of the 3 formulas they gave us for the half-angle formula, 1 minus cosine over sine, then we can get an even nicer simplification here by just recognizing that the alpha here is, the A in our formula is 5 alpha. And so that this is just the same as tan of A over 2. And that just goes immediately to a simplification of just tan of 5 alpha over 2. All right, so at least it looks like if you're just trying to simplify an expression with these identities, the expression they give you that you're simplifying has to really kind of look like the result of the identity, because you're going to go from the right side of the identity to the left side of the identity to do this kind of problem. All right, let's see if we can take a look at this last example in the time we have left. Verifying an identity. So now this is more like the ones we did before, where they give us a whole equation, an identity that we're supposed to verify. And you may recall throughout our earlier work in chapter 5, we had some different strategies for trying to do that. And the most common approach will be to take the more complicated side and try to work with it and simplify it and hope that that gets you to a point where you can match it up with the other side in the end. And that's what they go with here. So they take this left side of the identity that we're trying to verify because it's more complicated. And they say, well, what can we do with this? Well, we have 2 terms that are squared. So just algebraically, we can multiply that out. So they FOIL it out. Basically, if you have a plus b squared, then that gives you a squared plus 2 2ab plus b squared. And using that pattern, or literally writing these out and multiplying them, then that would give you the first term, sine x over 2, you would get that squared, plus sine x over 2 times sine x over 2 times cosine over 2 in the middle, 2ab, plus the b term, cosine x over 2 squared on the end. So they just foiled that out in hopes that then we could do something with that, in hopes that we could then simplify that in the same way using that pattern. All right, so then that leaves us with this thing. So now when you're looking at this and you're trying to say, all right, well, now how can I simplify this? This is like bigger than it used to be now. Well, then we have to think about other identities that we could use. And then first identity you're always going to want to look for to use when you can for simplification is sine squared plus cosine squared equals 1. So the first term is sine squared of x over 2. And the last term is cosine squared of the same angle, x over 2. So what they did is they brought both of those over here to the left and lumped them together in parentheses so that we could recognize that all of that, sine squared plus cosine squared, all of the same angle, can simplify down to just a 1. So that those two terms ended up just becoming a 1. Then when looking at this part over here, we then want to recognize that that matches our result for one of our half-angle formulas. I'm sorry, not half-angle, I just said the current one, the old one of our double-angle formulas that you would use double the angle in here. That sine of 2 theta is 2 sine theta cosine theta. So in this case, if theta is x over 2, then 2 sine x over 2 cosine x over 2 simplifies to just sine of double that, sine of 2 times x over 2. And then if you finally just cancel out those 2's in there, you get what you wanted on the right side. So we had to recognize a fundamental identity here of sine squared plus cosine squared is 1, and a double angle formula, which we did last section. And if you use those 2 modifications, then the left side, after foiling it out, completely simplifies down to the right side, and then we can verify this identity. Questions, comments, discussions about any of that?
Then like the formula is like kind of like square sine x plus square cosine x is 1, and square sine x over 2 and square cosine x over 2 is also 1. Then every like kind of like then like a square sine x over 1000 plus square cosine x over 1000 is also 1, like kind of that.
Exactly. So when you say sine, when you have just sine squared x plus cosine squared x, or I'm writing theta, or whatever you have in there, as long as these 2 are the same angle, then you're going to get 1.
Oh, okay. Thank you.
So since the theta is unknown, it could be 30 degrees each, 60 degrees each, or x over 2. As long as it's the same in both, then when you square those and add them, you get 1. That's
Okay,
exactly.
thank you.
Does that make sense?
Yeah.
Yeah, good question.